A box with mass m is dropped vertically on a moving belt that has a constant velocity of 1.5 meters per second. The kinetic friction coefficient between the box and belt is 0.1. How long does it take for the box to achieve the same velocity as the belt? When this happens, what is the displacement of the box with respect to the ground and to the belt? So first we need to figure out the time it takes for it to achieve the same velocity. So if we draw a free body diagram here. So here we have our box and below is the belt here. So upwards we have the normal force that is pushing up against the force of gravity. And now friction is going to be acting rightwards. So I'm going to move these letters real quick. So you have normal force, force of gravity, and then here we have the force of friction. And it's acting to the right because the conveyor belt is moving to the right at 1.5 meters per second. And it needs to achieve the same velocity as the belt. So when it starts, you can think that the box has a velocity of minus 1.5 meters per second relative to the belt. And the belt is, the friction is pulling it back. So that's one way you can visualize it. And then now we need to figure out the time. So by Newton's second law, we know that the force of friction is equal to mass times acceleration. And we also know that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force, which equals the coefficient of kinetic friction times the mass times the gravity. So now we can set these two statements equal. So we can say that the coefficient of kinetic friction times the mass times the gravity is equal to the mass times the acceleration. Now you'll notice that the masses cancel out, and the acceleration is simply equal to the coefficient of kinetic friction times the acceleration due to gravity. And that is the acceleration of the box once it is dropped. Now we just simply need to figure out the time. We can use this kinematic equation right here. This simply states that the final velocity is equal to the initial velocity plus the acceleration times a certain time interval. We know that the initial velocity is 0 since the box initially has no velocity and it's dropped vertically. And so we can just cancel this part of the equation. So we know that the final velocity is equal to the acceleration times the time. Well, it's asking how long does it take for the box to achieve the same velocity as the belt. So we know that the final velocity must be the same velocity as the belt, or 1.5 meters per second. Now we know what our acceleration is. We can plug this right here. So now we have that the time it takes for the box to stop is equal to the final velocity of the box and belt, or it's basically the velocity of the belt, divided by the acceleration, which is the coefficient of kinetic friction times the acceleration due to gravity. So if we run all the numbers in, get that it is equal to 1.5 divided by 0.10 times 9.8. And if you solve this, you should get that the change in time is about 1.53 seconds. And so that is the time it takes for the box to achieve the same velocity as the belt. So I'm going to erase everything here real quick. So we know that the time it takes to stop is about 1.53 seconds. So that's the first part. Now we need to figure out the displacement of the box with respect to the ground. Now we have another kinematic equation for this, and it's this one. It says that the displacement is equal to the initial velocity times the time plus 1/2 times the acceleration times the time interval squared. And then we just plug everything in. we really just need this part since the box starts out with 0 velocity, and this part of the equation is just simply equal to 0. And remember, the acceleration we figured out was the coefficient of kinetic friction times the gravity, or it is 0.10 times 9.8. So that is the part that we'll use. And so if you plug all the numbers in, you'll get it is equal to 1/2 of the acceleration, 0.1 times 9.8, times the time interval squared. We figured out the time was 1.53 seconds. So we're going to plug that right in. We're going to square it. Now if you solve this, the displacement of the box with respect to the ground is about 1.15 meters. So I'm gonna write that back up. The displacement of the box with respect to the ground is 1.15 meters. So now that's the second part. The third part is asking for the displacement of the box with respect to the belt. So to do this, we simply subtract the displacement of the belt from the displacement of the box relative to the ground. So it would look something like the displacement of the box with respect to the ground minus the displacement of the belt. Okay, so now finding the displacement of the belt is also not that hard. We use the same kinematic equation here, except the belt has a constant velocity, so we can ignore this whole part. It has no acceleration. So the displacement of the belt is simply equal to its initial velocity of 1.5 meters per second times the time interval of 1.53 seconds. So this gives you about 2.3 meters. So that is the displacement of the belt. Now we just plug this back into this equation to get the displacement of the box with respect to the belt. So it's like from the belt's view, what is the displacement of the block or of the box? So we just simply subtract the displacement of the block with respect to the ground, 0.15, minus the displacement of the belt of 2.3. Displacement of the box with respect to the belt, and this is simply equal to minus 1.15 meters. So if we write this back up, the displacement of the box would be displacement of the box with respect to the belt is equal to minus 1.15 meters. And this makes sense since if you were the belt and you were looking at the box, as it dropped down, it would begin sliding to the left until it reaches the same velocity and appears to stop. And this is how you would solve this problem here.